So this is going to be an example here where we have the indeterminate form 1 to the infinity. Again, 1 to any power is going to be 1, although we're looking at numbers that are approaching 1. And any number that's not equal to 1 to an infinite power is going to be infinite. Or if the base is less than 1, then if you have a number less than 1 to infinity, that's going to be 0. So we've got this indeterminate form here. To confirm this is indeterminate, we're going to check it. And so the inside part is going to go to 1 when we put infinity in for x. And the exponent is going to go to infinity, so we have 1 to the infinity. So what we're going to do is we're going to start by writing this function here that we're trying to find the limit of off to the side. We're going to do this separately, and then we're going to go back and we're going to continue this line later. Now, what did we do to that function? In the theorem that I just gave you, what are we going to do to this function? We're going to take the natural log. The reason we use logs for this, the reason we would even try to use natural logs with this, is because we have a nice rule about natural logs and exponents. Okay, all of these indeterminate forms involve exponents, and what's our rule with this exponent? What can I do with a natural log and an exponent? I can write that x out front, right? So this is equal to x times the natural log of 1 plus 1 over x. Now, if we take the limit of that as x approaches infinity, then what's going on here is we have this approaching infinity, this part here, sorry, I shouldn't have done that yet. This part here is going to approach the natural log of 1, which is 0. So we have infinity times 0. We'll rewrite that as a natural log of 1 plus 1 over x over 1 over x, so that we end up with the indeterminate form 0 over 0. Now, since we have 0 over 0 in our limit, what can we do? Use L'Hopital's rule. So we're going to take the derivative. This is not an extremely simple derivative on top, but we're going to have to use the chain rule here. So it's going to be 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, and so we get that. And then the derivative of 1 over x is going to be negative 1 over x squared. The nice thing about this is the negative 1 over x squareds are going to cancel each other out. And so if we try to put infinity in here, 1 over infinity is going to be 0. So we have 1 over 1, which is 1. Now that is not our answer. This limit right here does not equal 1. That's the limit of the natural log of this function. So our theorem says this is going to be equal to the limit as x approaches infinity of e to the natural log of f of x. And I wrote it like this just to kind of save some space and save some time. But this is really the same thing as the limit as x approaches infinity of e to the natural log of 1 plus 1 over x to the x. And if I try to put infinity in for x here, I have 1 to the infinity, but I already evaluated this part of the limit. The natural log of f of x goes to what? It goes to 1. So this is the same thing as e to the 1, or just e. So again, we take the natural log of this function, we take the limit of that, and we have to use L'Hopital's rule to do that, and we get 1. So the limit of our original function is the limit of e to the natural log of that function, and we know the natural log of that function goes to 1, so it's going to be e to the 1.